Hello, my name is Kyle Harris, owner of K2 Excel Solutions. I'm also a mechanical designer at a consulting MEP company. What we do is we create construction documents that contractors bid and build off of. And I've built this really powerful Excel spreadsheet that streamlines the design process and adds extra levels of analysis that heat load software doesn't do or doesn't do well. Now, this spreadsheet also generates VAV box schedules, air handling unit schedules, ventilation schedules. It does a lot of stuff that adds a lot of value and makes the overall the flow of the project is standardized, expedited, and it overall becomes more efficient. And if you like what I do in this video, I can create spreadsheets for you or your company to help streamline your design processes as well. So if you have any questions, reach out to me at k2excelsolutions@gmail.com. Enjoy. Okay, so what we've got here are some printouts of our heat load software. We have a warehouse, an office, fellowship hall, sanctuary, and classroom. These are 5 different building types that the total square footage adds up to 23,000 square feet. So this is a pretty large project. So the warehouse is going to be a single zone constant volume rooftop unit. The office is going to be a rooftop unit with a VAV rooftop unit which has downstream VAV boxes. There's going to be a fellowship hall rooftop unit that has an ERV. There's going to be dehumidification load for this due to the high internal latent load from all these people. Same goes with the sanctuary, and we're going to have a classroom VRF with a DOAS. Okay, so the goal is in 30 minutes, I want to schedule all the VAV boxes and create a ventilation schedule. I want to generate partial schedules so that I can send them off to the equipment rep for the selections. Partial schedules will be created for the rooftop units, the VRF, fan coils, and the DOAS. I want to also generate a schematic diagram that depicts the air movement through the rooftop unit and building in order to visualize the system from a high level. Okay, so first thing you need to do is paste the spreadsheet into the project folder and then change the project name . Okay, so let's get into it. Now, I know all of these tabs can be a little bit overwhelming. There's a lot in here. But that's what this first tab is for. It's to make the spreadsheet more manageable. So you're going to put in your project number, your project name, elevation, electric service available, let's say 2083 phase. Now, are we going to be doing new system ventilation, or is the ventilation schedule that we're going to be doing existing? So it's new, so type N for schedules that do not apply. So this is going to remove all unnecessary tabs. We're not going to have any cooling only. We're going to have VAVs with electric reheat. We're not going to have VAVs with hot water reheat. We're not going to have fan power boxes with electric reheat. We will have packaged rooftop units with ERV, and we will have packaged rooftop units without ERV. We're not going to have split system heat pump, so we can change that, and no split systems at all. But we will have VRF and DOAS. And watch down here, all of the unused tabs will go away. So there we go, more manageable. Next, you go to the very next tab, go to Hat Master. Let's bring these screens side by side, and let's start bringing in the information. All right, so you simply highlight the load, then go here, right click, and paste values. Be very careful not to Control C, Control V, because if you do that, this is what that'll look like. So you want to paste right here, but you don't want to do Control V because it makes it look ugly. So we're going to paste the values. So this is where we're bringing in the loads and the ventilation information from our heat load software, pasting it into the spreadsheet. Okay, so then let's also go to systems while we're here. So this is RTU-1 warehouse, and then this comes from all the way up here. With a 55, leaving air temperature, we'll say 54 degrees. And it's asking what's the humidity ratio when the air is going across the coil and is fully saturated. So all we need to look at is what is at 54 degrees fully saturated, 54, at a relative humidity of 100%, at an elevation of 1200, which is Pittsburgh. There is how many grains in that air? 65.06, and leaving the unit is 95. All right. Goodbye to that guy. Come back to him later if we need him. So then we go back to HAT Master. So we're done with this report. Then let's open up the RTU report. Same deal. Copy and paste. Control C, right click, paste values. Go down to the ventilation. Control C, right click, paste values. Then go to Systems, RTU-2, Office. All right. Now the reason we do this is because HAP tells us what the block load is and compares it to what the sum of the peaks are. So just because all of the airflow, max airflow goes to the spaces, if you add that up, that's not going to be the max airflow that a VAV unit is going to experience. So that is going to be this number, 6481 is the coil, so that's the airflow that the coil is going to see. 6481 and 7423. So that gives us a percentage of the coil. So equals that divided by that. So that's 87% of the unit is doing 87% of what if you were to add all the spaces up. So that is useful to know. So we're done with this one. Oh, well, this is going to be over here. So this is all the same, except this is going to be, it's a VAV unit, so it's going to be 55 degree leaving air temperature. All right. Next, Fellowship Hall. All right, go back to the HAT Master where we're importing all of the information. All right. Control C, right click, paste values, and then grab the ventilation information. Okay, and same as with the other ones. $43.83, $43.83. All right, done with that report. Again, we're just importing information from our heat load software by copying and pasting from the reports directly. I usually put a couple spaces between there just to make it visually easy to identify where the reports start and stop. Okay. This is saying, okay, right? It's going to be the same as it's a single zone system. This one's just going to have an ERV. Okay, so we're done with that. Now let's continue on with this. I added this feature recently, so previously I would have to go like this, RTU-1 for all of those. And then I would have to say 135A, 135B, and I'd have to type it all out. And this is VAV 1-1. That applies to those two. And this would be 110, 107, and this is on RTU-2, RTU-2, and this is our RTU-2, but this is now VAV 1-2 and 103, so you'd have to keep doing that. 102, and it's VAV 1-2 because of that, and this is VAV 1-1 because of that. And what you do here for single zone constant volume systems, the system and the zone are going to be the same, like that. But that's kind of tedious, so I was like, you know what, I'm going to write a macro to allow the spreadsheet to figure it out itself. So you push the auto indexing button and it does it itself. Okay, so we got to clean it up a little bit here. Get rid of this warehouse. That's it, and RTU-1, RTU-2. It does not do the system. Okay, so now all of the information has been imported. Then you copy that, Control-C, and go here and go to cell A6, right click, paste values, and while it's already highlighted, go to Data, Sort, Continue, uncheck that box, so it's going to put those in order. Then you go to the Zones tab, all right, and you copy, right click, paste that, and do the same thing. Okay, and then I like to hide this. Okay. So this is all of the airflow that goes to the space right here. You can change the temperature. You can change the adjustment factor. So if you're looking at this and this space is 0.44 CFM a square foot, you can do an adjustment factor and say 150%. Okay, now we're at 0.66. So you can look at the CFM a square foot and then make adjustments in order to accomplish that. Okay, so if I wanted to have some exhaust in some spaces, like this women's restroom, so let me freeze this this row here. So there's women's restroom right here. So this is exhaust. You would type in right here. So let's say there's 2 toilets, so it'd be 100 CFM. Okay, and let's say this space has pressurization of 50 CFM going out of the building. So minus 50 going out. We'll just throw minus 50 in a couple spots. Just because we want our building to be positively pressurized, which means air is leaving the building, which is why it's saying negative. And let's also put it there. All right. If there's any other bathrooms, I can. So that appears to be all the bathrooms. But let's just say there's more exhaust in some other rooms as well. This is just so that you'll be able to see a schematic diagram that depicts air movement through the rooftop unit in the building to visualize the system. This is why I'm putting this in, because it'll build the schematic to you'll be able to visually see this air movement through your system. Okay, so next you go to zones. So RTU 1, so this is where you size your VAV boxes. So RTU 1 didn't have VAV, only RTU 2 did. Okay, so these are all the VAV boxes. So what you'd say is, let's say all of them have reheat. So you say yes for this. And then it tells you what the size VAV boxes are. And it also tells you what the kW required to condition is based off of the heating MBH required for each of those zones added up. But this is the kW, minimum kW in order to meet the heat load, and I like to round. So instead of 3.8, I'm going to put in a 4 kW. Instead of 5.7, I'm going to put in a 6. Instead of 1.6, I'm going to put in a 2. So I just continue to do this here. This is where the spreadsheet really is powerful in assisting the designer. We'll say 2, that's 78 degrees. So that's telling us what the leaving air temperature is going to be. So I would like to, you can either increase the kW to 3 kW or 2.5 kW, but then you're putting too much kW in. So another option that you can do is go over here, and this is the heating airflow, and the default is 70%. So if you wanted to have warmer air, you could make your leaving air temp. You can make your heating airflow less. So let's make it 60%. All right. So now we're at 2, and so when this was 2 earlier, it resulted in 78 degrees. And when I drop this down to 60, now it's 80, almost 83. So there are multiple ways to address that cold air. You can either add more heat in kW, or you can reduce your heating airflow. I chose this in this case to reduce the heating airflow. So here's a 4 kW. Again, we're getting really cold air. We're meeting the heat load. So I'm going to do a combination. I'm going to bring that down to 50 and make this 3 and make it 4. Okay. So that's how that works. And we've already seen this tab. So here is where it sizes the HVAC equipment. So we have an RTU-1. So RTU1, we have an RTU, so move, copy, paste before that tab, hit OK. So we're just duplicating, move, copy. So that's 3. And last one is RTU4. It is important to rename these tabs. for the purpose of macros that auto schedule to work. All right, so RTU1 is there, RTU2, RTU3, and RTU4. So this is saying the outdoor air that is required is 490 CFM, and this is saying the cooling airflow is 1590 CFM, and the dehumidification for this warehouse airflow is only 350 CFM. Okay, so we're gonna size for 1590 CFM. And what you can see when you do that, this is telling you you need a 5.3 ton unit. Oh, that's the ventilation airflow of 490. 490, 1590 is the supply airflow. And this is, so I'm pulling this from right here. So this is where it's sizing it. 5.3, 44, 19.7 is the latent, and the heating output is 68.7. So the square foot per ton is 725, and your CFM per square foot is 0.4, and the GPM for the condensate is almost nothing. So then you would go back and say, okay, so that's the absolute minimum performance, but what if I made it 500 just for nice round numbers, and 1600? How does that change the capacity? So 500, 1600, and this is what I would schedule. 5.4, 44.4, 20.1, 69.6. That's it. Okay, so this is telling me that I need an economizer, but I don't need energy recovery. I don't need a return smoke detector, and I don't need a supply smoke detector. So next. So this is saying I need 1600 CFM, and this is for an office. So here you can see that the sum of the peaks, the airflow is 6800 CFM, but at my 87% of the peak is my block load for my unit. So I need 6000 CFM at the unit. So I have 6000 CFM, and my dehumidification airflow is only 2090 CFM, which makes sense because this is a normal office job. So there's not a large dehumidification load. Now, where is this dehumidification load coming from? That's right here. That's the question. That's based on the dehumidification analysis over here. So what you do is my default is 75 degrees during cooling, and humidity set point of 55% relative humidity. And you get out your psych chart, and you can put in these two pieces of information. You'll see that the resulting humidity ratio is 74.7. So 75, 55 at 1200, the grains per pound is 74.7. So that's where that comes from. And based on the leaving air temperature, which is, so this is the humidity ratio off the coil, and that is coming, so this 65.1 is coming from here, which we found already right here. This is for the office. 65.1 off the coil is the amount of moisture in the air. So based off of the delta grains, this is the amount of airflow that's needed. So the grain depression is 9.6. It's the difference between the space and the and the humidity in the air. The space humidity required in grains compared to the humidity ratio of the supply air. Okay. Oh, but also keep in mind here, so this is another input that's required for the dehumidification analysis, is the amount of internal latent load. So if there was no latent load, all you would need to do is bring air that has 74% 74.7 grains in the supply air, because if you start bringing in air that has more grains than that, you're going to start humidifying the space past this set point. Okay, so if you wanted to, so what you need to do though is, because there's actual internal latent, you need to offset that internal latent by bringing air that has even less than 74 grains in the air, and that in this case is 65. So if I change this to office work, you can see that the amount of airflow required to condition to dehumidify was 2,000 something, and now it's 3,580. Seated at rest, people aren't putting off as much latent load. Office work, they're putting off a little bit more, so that's why the dehumidification airflow increased. All right, let's keep going here. 1,600 CFM and 6,000. The capacity is 19.9, 162, 76.5, 241.7. So here we're looking at almost 400 square foot per ton, which is exactly what you would basically expect for an office project. So we're just going to go exactly with that. Those numbers seem pretty nice. All right. Next, RTU3. So this is 2050, is the ventilation airflow. And this is saying for people seated at rest, we're running into a problem. We've got the cooling airflow, 4130 CFM, is less than what's required for dehumidification. And these people are seated at rest, so it's going to be tough to be even less than that. So you could either increase your leaving air temperature, your humidity set point, but I would not increase it past 75, 55. So for this, you can either say, okay, yeah, let's bring in 4,580 CFM, or you can say, well, maybe I can get colder air off the coil. So if you did that, you would go here to, so this is for the fellowship hall. Let's say we get 53 degree air. So what is 53 at 100% relative humidity? And that is 62.68 grains from right here. So now we need 3,670 CFM. So that makes me feel better. So now instead of 4,580, we need 4,130. And this is assuming a 2 degree delta T due to the sensible heat gain from the motor. So we have 55 degrees out of the unit and 53 degrees off the coil. That's with a draw through unit, a 2 degree sensible heat gain is reasonable. Okay, so that's it for that one. And we're looking at around 18.8 tons, 131.1, 94.4, 233.3. Oh, this is 2050. For 130. 233.3. Okay, now for the design, so that was the minimum, but for the design, let's increase this to 2100 and this to 4200. Okay, so now 2100, 4200. Now we're at 19.2 tons, 133.8, 96.3, 238.1. And our square foot per ton is 263, which makes sense because this is a lot more densely populated. This is saying I need energy recovery due to the climate zone that I'm in. If I went to a different one, the climate zone would change depending on whatever ratio. So in 5C, energy recovery is not required, but we are in 5A, and energy recovery is. So that's our climate zone. It is required. Economizers required, and return air, return air, and supply air smoke detectors are also required. So that's done. And last but not least, the sanctuary. And this is the same thing is happening here. So this is saying we need 8,890 to dehumidify, and we need 5,740 CFM to cool. So we definitely need to lower our leaving air temperature to 53, which we know is this. So now we're down to 7,130 CFM. And so that I would like to get it down to 7,000 CFM. So if you go to the systems, let's say 60 or 52.5. 52.5. 61.5. All right. So yeah, we're down to 6,500 CFM, which is pretty good. But you can see here, this is 485 people seated at rest in a sanctuary. The latent load is what's driving the airflow requirement, not the cooling airflow. So it's definitely critical for when there's a situation, whether it's a gym, a fellowship hall, a sanctuary, anything that has a lot of people packed in, or people putting off a lot of latent loads. They're sweating, working hard. Would be an application for a fitness center or a gym. The latent load is going to be oftentimes the driver in the airflow requirement that the unit needs, not the cooling requirement. So very important to differentiate between the two and to be aware of how to calculate this. And my spreadsheet does that for us. Okay. So we're just going to go with the same, what was that, 3610 CFM, 3610 and 6,500 capacity. It's right here. We're going to do the same for the minimum and design. So here for the sanctuary, we're at 165 square foot per ton, and the condensate GPM 0.3. Not very much flow. And again, we need energy recovery, economizer, smoke detectors in both the return airstream and the supply airstream. Okay, so once the rooftop units have been sized, you can then go on to the ventilation tab. And this is the ventilation schedule that you would be able to copy and paste under your drawings. The only thing that is missing is the ventilation classification. You just have to manually input that. So this space is a corridor, so you have to pull from the drop-down corridor. Field services is an office, server room, we can call that. Storage unoccupied. Training room is essentially a conference room, and women's restroom is a public bathroom. Okay, and then you have to, for bathrooms, you have to put in number of fixtures. There are 2, so continuous exhaust or intermittent exhaust. If you change this to intermittent, this will go from 50 to 70. But I'm going to design around continuous. Okay, so ventilation schedule is done. You can copy, paste it on your drawings. So then you have your VAV schedule. This is what the VAVs with electric reheat. We've already sized all of this mechanical equipment. We're merely pulling in the data from other parts of the spreadsheet and then making it organized in a way that's easy for contractors to bid on. Okay, so let's go to where we size the VAV boxes, which is the zone tab. So you're going to copy the VAV boxes with electric reheat. I'm going to copy those into the electric reheat tab. copy, paste the values, and then you're able to copy and paste that on your drawing. All right, now we have the package rooftop unit schedule with energy recovery. Now this is a partial schedule that we're going to send out to a rep for selection, but we need to give the performance requirements that we've already worked out and sized in the previous parts of the spreadsheet. So which two had energy recovery? So you would go back here, and energy recovery required for number RTU4 and RTU3 as well, right here. So you just type that in, the name of the tab, RTU-3, RTU-4, and then magic import. Okay, so there you go. You're ready to send your partial schedule out to a rep to get a selection. Then you go to the packaged rooftop unit. This is the one without energy recovery. So all you do, RTU-1, the name of the first tab, RTU-2, and then magic import. So this includes everything like the estimated number of tons, where it serves, airflow, supply airflow, outdoor airflow, entering air conditions, required coil leaving air conditions. We have total MBH, sensible MBH. We have in heating, again, entering and leaving air temperatures and capacity. And we even have notes here. So schedule, the schedule says that notes 1 apply to the first one and notes 1 and 2 apply to the second one. So provide economizer with barometric relief, if applicable, refer to notes. So first, they both need economizer, but only the second one, RTU2, needs return air and supply air smoke detector. Okay, and that's it. So now let's move on to the next portion of this, which is the VRF and DOAS. So this is done entirely different. Everything is self-contained. It has to do with VRF and DOAS. So let's pull up that. Let's pull up that report. Okay. So let's make this a little smaller. So it says copy and paste zone peak sensible loads. So you find the title zone peak. Oh, right here. Look at that. Copy. Paste those values. Okay, and then it says, oh, copy and paste ventilation summary. Okay, so we got to find the ventilation summary. Where's that at? Oh, look, it's right here. Copy. Paste those values. All right. So the only thing remaining is the latent load. So this is only the sensible load. We need to bring in the latent load as well. And that is found in the individual space printouts. So FCU1 has 7,350. FCU2, 7,350 as well. FCU3 has 2,520. FCU4 has 2,100. FCU7 has 4,338. FCU8 has 2,206. 9 has 2,206. 10 has 410. 11 has 4,787 BTUs. This is all the latent load. 2,069 and 2,069 there. Okay. So now you are done with that report. So here you get to decide how much of that load, how much of the latent load is going to be taken care of by the ventilation air, how much is going to be taken care of by the VRF unit. In my opinion, good design practices have to have the internal VRF unit handle all of the latent load and have the DOAS unit handle the outdoor air load in order to dehumidify it to a point where you're not humidifying the space with the ventilation outside air. So the VRF equipment is ready to send to a rep. You copy and paste that, send it to them. Okay, so this is what we have here. For dehumidification, all right, we at the very least want 75 degrees at 55% relative humidity. Okay, and this is the humidity ratio that's associated with that. This tells you, so you could say this serves the classrooms. So the supply airflow is 2030. And here you're saying, so I need at least to my ventilation airflow needs to get down to at least 74.7 to not humidify the space with the ventilation air. Okay, so let's pull up the site chart. So what you would do is you would say, okay, so 74.7 is the grains per pound, and at 100% relative humidity. So at what is the associated coil temperature that's fully saturated is there 74.7 grains, because that's the temperature at the very warmest that you can cool down to in order to not humidify the space with the outdoor air. And that would say 58.9 degrees. So I don't want to do that. I want to get a little bit extra dehumidification with my outdoor air. So what I'm going to do is I'm going to say, all right, I want 55 degrees out the unit, 100% at 1,200 feet. What is the grains per pound for that? So that's 67.5. And that's what's here. So you would send this to the rep as well. And that is it with regards to sizing equipment. Now there are a couple other nice features that I have built into this spreadsheet to show you a schematic diagram that depicts air movement through the rooftop unit and the building to visualize the system as a whole. Okay, so where that is over here. So you can see exhaust air, relief air going out, outdoor air going in, mixing with this much return air, and all of the airflow, the temperature, and the humidity in each segment of this is seen. And you can see how this all happens. Then it goes through the mixing damper, goes across the cooling coil, then goes across the supply fan, picks up a degree of sensible heat gain, but the overall humidity in that air is still the same. Goes to the space, tells you the set point, and it also says how much is exhausted, how much is transfer air from other systems, what the pressurization air. In this case, it's none because in the spaces I didn't assign it. I could. So let's filter down RTU1. So we didn't have any. So if we said we want some exhaust, 100, let's say 100 CFM of exhaust in that space, we want 150 CFM of pressurization air, but it's got to be negative because it's going out. And transfer air, let's say we have 200 CFM of transfer air going in from another system. So all you do is go back to RTU1. You can see how this updated because of that. So this is purely dynamic. As you make changes to the spreadsheet, this automatically updates. And it does it for all of the units. So that's pretty cool. If you have a person that isn't really good at visualizing what is going on in the system, it's a great tool to help them really break it down visually. So that is everything.